Hello, everyone. Thank you all for joining me today. I'm Judy Piper. I'm one of the engineering leads at C Labs and also the talk show host for this Tech Talk series. Celo Tech Talk is one of many Celo Foundation's effort to share and spread Celo technology knowledge with the growing Celo community. For this reason, the first Celo Tech Talk back in April was to introduce the Celo and high-level overview of Celo full-stack architecture and design by yours truly. And from that, we delved deeper into different building blocks of Celo during subsequent talk. Celo's mission is to build a financial system that creates the conditions of prosperity for everyone. Based on the user feedback, we realized early on that we needed to build a mobile-first full-stack solution. We gave a technical deep dive on Valora, Celo mobile wallet that highlights the vision of building a truly accessible financial system. We went to deep dive into Celo's consensus system, proof of stake, and how Celo network works. We also talked about how validators are incentivized to operate and run the Celo mainnet in a secure, resilient, and reliable way. We also talked about stability protocol, governance, price oracle, and phone number privacy, SDK, Celo blockchain deep dive, and many more. In the last two tech talks, Barbara from DevX team showed how you can build your first steps on Celo, of course. By the way, all these Celo tech talks are available on YouTube, so please check them out if you missed them, and let us know if you have any questions. In this tech talk, we have a Bogdan Dumitriu, a Berlin protocol engineer at C Labs. We'll talk about how we made onboarding to Celo Feeless. Welcome, Bogdan.
Hey, everybody. I'm happy to be here. Like Judy said, I'm Bogdan. I've been with C Labs for like about half a year now, maybe a bit more, working in the economics circle in Berlin as a protocol engineer. And I've been kind of interested in the crypto space for the better part of 4 years, I guess. Essentially, since Ethereum came out, that really shifted me towards this direction. And I'm really passionate about Celo's mission. That's what brought me to it. I think, there's a lot of talk about banking the unbanked in the crypto world, but I think Celo is really putting their money where their mouth is, so to speak. And yeah, today we're going to talk about Feeless Onboarding, which sounds a bit cryptic, but it's about how our users onboard to our platform using Valora and kind of what it takes to make that process a bit more inclusive and more user-friendly at the same time.
We have a lot to cover today on the Feeless Onboarding feature. So if you have any questions, please post your question on the Ask a Tab question tab that you see on your screen, bottom of your screen. All right, take it away, Bogdan.
Cool. So, first of all, let's talk a bit about how Valora works, how the identity protocol works, and what actually means to onboard on Valora in our system. Taking the step back, like Julie mentioned as well, our mission is to build a financial system that creates the conditions of prosperity for everyone. So when we think about the conditions of prosperity, we think about a financial system that's super easy to use and inclusive. And part of that is having the right tools to interact with it. So with that in mind, we've spent a lot of effort to build Valora, which is like mobile first wallet essentially, but like a payments app. It tries to be very easy to use and very approachable. So like you can easily send the money to your friends, receive payments, and build on top of it as a nucleus of interaction with the Celo blockchain, but in a way that's very user-friendly and doesn't feel like you're actually dealing with a blockchain. And when we're transferring money on the blockchain, a lot of the time, you need to do some weird things. Like when you're sending money to your friend the first time on Ethereum or anything else, you kind of have to handle these addresses which aren't so nice. Of course, it's way nicer to send money to your contacts in your phone and have them get that directly. But of course, in the back of that, we still need to handle addresses and everything like that. So part of the identity protocol in Celo is building a mapping between a phone number and an address. Cool. So when you have like a centralized system like, I don't know, PayPal, Venmo, Revolut, whatever, or anything else maybe that's not payment related, when you want to link your phone number to your account, it's pretty straightforward. You tell to that server that, hey, this is my phone number. The server says proves it by sending you an SMS. You use that SMS to put in the code, and that's kind of it. The server, the centralized service, kind of handles that mapping. And then when another user wants to send you money in the system, they just say, oh, send money to this user with this phone number, and they find you and give you the money. But that's cool. But at Celo, and in blockchain in general, we're kind of a constellation of different players that work in a decentralized fashion. So if we kind of look at this chart, we start at the edge with light clients, which are actually running on the phones of our users in Valora. These interact with the full nodes when you go in. These are nodes that are more powerful and have more of the state actually have the full state of what's happening, and are used to kind of propagate that out to the network. And then when you go even deeper in, you have the validators, which are the nodes that are actually generating blocks, and they're kind of making everything happen. And these are essentially the trusted nodes in the network, the most trusted nodes, because they have an incentive to behave correctly, because they will get slashed if they don't. So our identity protocol kind of uses these validators. So because we trust them and it's in their instinct to behave, they get a service attached to them. So apart from just running their normal blockchain client that interacts with the rest of the nodes, they have a service that can handle this part of sending SMSs and verifying all of that. So yeah, this interacts with the phone, and then the node itself interacts with other nodes. So let's look at how it works in practice if I want to link my address to my phone number on Celo. Basically, I start by interacting with the smart contract and saying that, hey, I want to link this address. And then I get back a response that, okay, you have to talk to these 3 validators. Okay, why 3 validators? Well, one validator saying that your phone number is right gives you 1 attestation. 3 validators agreeing, like getting 3 attestations, give you a valid mapping. We need to do this because this is a decentralized network. So if one validator wanted to act wanted to be Byzantine, essentially to act as a bad entity, he could create an attestation for any phone number and basically create a mapping. And if one validator behaved nefariously, he could then, other people transferring money to that phone number would get to this mapping that he added. So we increased the number of attestations required so that basically it would be harder for 3 validators to collude. And this is a number that we're still tuning. We're figuring out what the best mapping is. Cool. So that's why we need to talk to 3 validators. So the next step is similar to what we're doing in a centralized service. We tell the validators, hey, I want to prove that I own this phone number by talking to the attestation service. We get some signatures back in an SMS that we can then validate. We send them to the chain and be like, okay, I talked to the validators, here's the signatures. And the smart contract says, cool. Well, I mean, this is kind of what I explained, but what's happening, the process is way more complicated than that because of privacy. And Judy mentioned we have a nice Celo tech talk about how do we do phone number privacy, because you can't just send your phone number around, because of course that's not cool. But with the simplification aside, what we end up with is the fact that, okay, now we have 2 users, they have some phone numbers, and we have a mapping between those phone numbers and their accounts. And then when sending money from one to another, we can just reference the phone numbers and the money is going to go to their accounts, which is great. But there's a catch. So when the validators send SMSs, that actually costs them money. And because this is all happening in like a permissionless decentralized protocol, you can have bad actors that just ask for validations, for attestations, and they just essentially end up spending the validators' money, which is not great. So the solution that we use, and yeah, this is to actually have the user pay for the attestations. When we think about operations in a decentralized network, this kind of makes sense because it's the same thing when you're interacting with smart contracts or doing anything. You have to pay for the gas. There has to be like an economic incentive for the system to align itself and reach like an equilibrium. So what we're doing here is we're actually putting a cost on this attestation, which means that the a bad actor would have to actually pay to get these SMSs. So he's not really incentivized to do that because he won't be gaining anything from that. So when we're saying before that the smart contract says, okay, talk to these validators, in the background, each one of these validators actually gets these 5 cents to kind of pay for those SMSs. Cool, but okay, what does this mean from a user? So I just downloaded Valora, it's my first time. I want to start setting it up. And then I'm like, okay, I need to pay to verify my phone number. This is not a great experience, especially because you don't have any funds at the moment when you're downloading the application. And while 15 cents might not be a huge amount of money, we're talking in a very global context. And 15 cents means different things to different markets. So the question is, how can we improve this? How can we find a balance between keeping the decentralized identity protocol with its primitives and its insurances, but also giving Valora a good user experience? And this is kind of the crux of the problem that we're trying to solve. Cool. With that out of the way, let's get into the fun part. How did we fix this problem? So yeah, the first thing we thought about is that, okay, we need to somehow help the user pay for those funds, for those attestations, because we don't want to remove that constraint from the system, because it's not just us consuming the system. The system is decentralized, it's consumed by everybody, and it needs to keep those invariants. But we want to help users with Valora on board. It says, okay, let's have a subsidy fund. And let's say the user starts up, it's like, hey, I'm a new Valora user and I want to link my phone number. And then the subsidy fund goes, okay, cool, here's 16 cents, 15 cents to pay for the attestation, and 1 cent to pay for transaction fees, because as we know, actually running that logic, you need to pay for transaction fees. Cool, okay, then I would go and say like, yay, I can do this, I can link my phone number, I have the funds to do that. But there's problems. Like if we just go around giving money to everybody, then people can just not validate and get the cents. So we thought about it and we're like, what if we create some tokens that can be sent, can be used to pay for attestations, but can't be used to do anything else unless you're a validator. And if you're a validator, you can change those tokens back for dollars. This solves part of the problem in the sense that there's no longer an incentive to collect those tokens. But yeah, you still have to pay for transaction fees. And it also, having those tokens adds some complexity to the whole protocol, which is a bit unwarranted for this, and it's not very elegant. Yeah, so when we take a step back and think about what goes into this attestation request, we can think about it like, okay, I need to mail something somewhere to ask for like a request, and I need to like sign some forms that are like my request. Then I need to put that in an envelope, put in some money to pay for it, and then I need to put a stamp on the envelope and send it, right? So we're talking about the payload of the request, the money that's needed to honor that request, and then the gas cost, basically. And in general, like in Ethereum as well, we have this coupling from who wants to perform an action and who's paying for that action. So essentially the stamp and what's happening inside it. This coupling happens essentially because how we're treating these primitives in Ethereum and Celo as well, message sender and transaction origin. Essentially, who's actually originating the transaction and who's the current sender when you're talking to a contract, a smart contract. The gas is always going to be spent by is always going to be paid by the transaction origin, and the sender in a lot of smart contract logic is the one that's performing an action. So we can think about it like who wants an attestation and who's paying for that attestation. But luckily, there are solutions for this out there that have been discussed. And one way of kind of dealing with this coupling is by introducing meta transactions, which come to the rescue. So let's use meta transactions first to talk about how we can subsidize the gas fee. Um, and then we can actually look how we can do the attestation fee as well. But the gas fee is like a good start because it kind of it's the base use case for meta transactions. Cool. But before we go forward, I want to simplify a bit because I'm going to be running through a lot of examples in the following slides. I don't want to use addresses. So instead of addresses, I'm going to use these sort of labels, which are like 0x and something and 0x and something. But when it's blue, it's referring to the externally owned account, which is the one that's backed by a private key and the one that people actually own and use to operate the network. And when I say when it's yellow, it refers to a smart contracts address that lives on the blockchain that accounts interact with. Cool. So let's look a bit at how a transaction is actually sent and how gas is paid. So if I'm Alice, I want to request an attestation. So I start building a transaction. This is like the basic payload needed to define a transaction. What am I calling? I'm calling the attestation contract. I'm not passing in any value, any like native token of the network value. And I have some data there, which is like a hex string, which encodes some logic. And this is like a native chain transaction. I need to sign it as well, include the signature. Then I pass it to the chain. And awesome, it executes. And if you look a bit about the context, we have Alice is a external account calling this attestations contract. And inside of the logic of the attestation contract, the message sender is Alice. And the transaction origin is also Alice, which means that Alice is paying for this transaction. And Alex is also benefiting from the logic by being the message sender of that transaction. If we wanted somebody to pay for a transaction, like we would want things to look somehow like this, in the sense that I have a payer who's calling that attestations contract, but I want Alice to be the one that's benefiting from the attestations contract. And this is impossible to do with how the network is structured. This is like, yeah, an example of how we want things to look like. But the thing is, we have a way of going in that direction when we think about how contracts interact with each other on in the EVM and on the networks. So if somebody is calling a function on one contract, and then that contract is calling another contract, then we get kind of this arrangement. In the first contract call, the sender is the payer, and the origin is the payer as well, which is always going to be the case. But in the second call, the sender is actually the previous contract, and the origin, the one paying, is again the payer. So in this second contract, the one that could be benefiting from the actions of that contract is actually the previous contract. So it looks like we can have something in the middle there that somehow represents Alice. And in that way, we could have an action that goes through this contract and to the attestations contract. And this contract benefits from this. And then the payer can be anybody. Cool, but yeah, what could we have there? So this is where something that we call a smart contract wallets come into play. Basically, a smart contract wallet is just a smart contract that is tied very closely to one external account, which is the signer. In this case, Alice has the smart contract wallet, and she is the signer of that wallet, which just means that this contract can act on behalf of her, and anything that this contract manages to do or obtain can be controlled by Alice. So it's just kind of an extension of Alice's externally owned account, but which lives in a smart contract. And this gives us more power on how we can structure interactions with other smart contracts. So with this in mind, we can structure things like this. So Alice has the smart contract wallet, and anybody can make a request to that wallet and then somehow make that wallet act on the attestations contract. And we get this nice thing where the message sender is that wallet and the transaction origin is the payer. So he's paying for all the gas in this. So let's take a look at how this works. We have Alice, and she has this smart contract wallet that we talked about, and she wants to make a request to the attestation, and she doesn't want to pay for the gas. Well, she starts by building that transaction similar to how she did before, but you see here that I marked it as a meta transaction and it uses a bit of a different color. This is because it shares a lot in kind of abstract logic with what a native transaction is, but it doesn't behave the same. It's going to be evaluated on chain. But let's see how this works. She still has to sign it the same, but instead of passing it to the chain, she now passes it to this new thing that we have here called the meta transaction relayer. This relayer is just a piece of software that controls its own externally owned account, Xerox Relayer, and it can act as the payer that we were looking at earlier and execute these transactions on chain while paying for the gas of that execution. So what happens? The relayer gets that meta transaction and actually starts building a native chain transaction that's destined to Alice's smart contract wallet, no value either. And inside of that data for that transaction, it actually nests what it gets from Alice as this meta transaction. It signs it the same and sends it to the chain to be executed. And when we look at this execution, basically the relayer calls Alice's smart contract wallet, where Alice's smart contract wallet can determine that what's passed in is a valid meta transaction that was signed by Alice. And this is super important because only Alice can act as the smart contract wallet, and that's why we sign it. And then it just reads what's inside of this meta transaction and executes its logic by calling the attestation contract. And awesome, this is exactly what we wanted. So we look at this little comparison, how it looks like when Alex is interacting directly with the chain, and how it looks like when Alice is interacting with the chain via her smart contract wallet and powered by the relayer. So we kind of get this same interaction here. That's what we want. And in one situation, the attestations are owned by the smart contract wallet. And in the direct situation, the attestations are owned by Alice. But it's cool because we have this link that I mentioned between the two. So we're fine with that, which means that, yes, we just managed to create attestations without paying any gas for them. But there's still the pesky matter of the attestation fee. So in order to kind of take care of this, we need to remember that when we were linking our address, we had to pay 15 cents. But now we're doing this, which is a bit different. Like we instead of linking our addresses, we want to link our smart contract wallets, but we still have to pay 15 cents, even if we go through the relayers. So in order to kind of understand how to fix this, let's take a step back and look at the attestation fee. The attestation fee is paid in CUSD, which is an ERC20 token that we have on Celo and which is pegged to $1. It's part of our stability system. There's a really nice TikTok on that. I recommend you watch it. And in order for the attestation contract to actually receive that CUSD, two things needs to happen. The sender in that transaction needs to have previously approved the attestation contract to take that money from the sender itself. And of course, the sender needs to have that balance. I wrote there n times 0.005 because we talked until now about 3 attestations all the time, but you can actually request more or less depending on how many you need. So essentially, any request comes with a number of attestations, and you need to have enough funds for those attestations. Cool. So we know that this needs to happen, and then we know that this is how the transaction looks like, which means that here, not message sender, more specifically, Alex's smart contract wallet needs to have approved and needs to have that balance. Shit, this is not great because we need to, there's no way to work around the fact that at some point, the smart contract wallet of the user needs to have those funds. But lucky enough, there are some other advantages to using meta transactions that we can use to work around this need. One of these advantages is the idea of atomic meta transactions. and atomic meta transaction batching more exactly. So what are we looking at here? We're looking at a transaction that's sent towards Alex's smart contract wallet, and it's coming from Alice herself. And nested inside, instead of having just one meta transaction, we have three meta transactions. And if you see, there's no more signatures associated with the meta transaction. This is not an omission. This has to do with the fact that when Alice herself is calling her smart contract wallet, she doesn't need to sign those transactions because she is the signer of that wallet. So we can verify that the native transaction is coming from her. But when somebody else, like the relayer, is calling the smart contract wallet, the meta transaction needs to have a signature, right? Like I was saying, the relayer is not the signer, but if Alice is calling, she is the signer. So that's okay. She doesn't need to pass. So how is this transaction actually unrolled? So if you look at it, we have Alice calling the smart contract wallet, and then the smart contract wallet calling each of these other contracts in turn. Cool. So what happens if one of these meta transaction fails? Well, if any part of a transaction reverts, then the whole thing reverts. This is just an invariant of how things are executed on chain. So basically, we know that this is an atomic operation. Like any batch of transaction that we format is going to be an atomic operation. The next thing that we can do with meta transactions is we can actually nest them, which is another interesting property. So what we're looking at now is a transaction that's from Alice to her smart contract wallet, inside of which we have a batch of two transactions. One is a call to a contract, and the other is a call from Bob's smart contract wallet to another contract. So yeah, let's break it down here. What do we have? We have two externally owned account, Alice and Bob. They each have a smart contract wallet, and we have two more arbitrary smart contracts that we interact with. And if we break this down, we have Alice as the root calling her smart contract wallet, which calls the contract one, and then calls Bob's smart contract wallet, which executes another meta transaction signed by Bob to contract two as Bob. So this is very interesting. How can we use these primitives to build a nice subsidy model? Yeah, before that, we need to do one more thing. What we talked about now, we had the relayer, we just acted as an externally owned account, but now let's actually give our relayer a smart contract wallet itself. That way, the relayer can take advantage of that batched feature of meta transaction. So it can also execute multiple transactions. Cool. So let's go back to this. We wanted to pay CUSD for the attestation fees, and we wanted Alice smart contract wallet to have that money. Well, first of all, when requesting the attestations, Alice needs to create one meta transaction for sure. That's towards the attestations contract in which she's requesting these attestations, right? This is the one that in order to execute, we need all those preconditions to happen. Cool. Alice can easily sign another meta transaction which approves the attestations contract for like whatever 15 CUSD cents. Okay, this is fine. We can have these two meta transactions and we can pass them to our relayer. And now we just need one more thing, basically. We need to give Alice's smart contract wallet funds. Cool. So let's actually do that as a meta transaction of the relayer. So we're doing a transaction to the CUSD ERC20 contract, and the data of that contract is that we want to transfer those funds to Alice's smart contract wallet. Okay, now that we have this, we just need to introduce that wrapping that we talked about earlier. So we need to create some meta transaction towards Alice's smart contract wallets in which we nest the ones that Alice signed. And then let's just batch all of these three into one native transaction on chain that the relayer calls on its own smart contract wallet. I know this looks kind of funny, but it actually does the job pretty well. So let's break it down. We have the relayer calling its smart contract wallet, which it's telling it to execute a batch. The first action is a call to CUSD, which transfers money to Alice's smart contract wallet. The second call is a call to Alice's smart contract wallet, which results in the call to CUSD to approve the transfer of those 15 cents it just received to the attestations contract. And then the third one is to actually request those attestations and pay for them with the funds that she just received in this atomic transaction. And like we said, the cool part is that if anything fails, like the attestations can't be requested for whatever reason, then everything fails, which means that there's no way that those funds reach Alice's smart contract wallet and aren't spent in the same transaction, which is awesome. It's exactly what we wanted, right? I know. We got everything. Cool. So let's see how this looks like in the end. The user comes, is like, I want to link my smart contract wallet to this phone number, tells the relayer creates that very convoluted meta transaction, passes it to the protocol, and all is well. Nothing changed. The protocol sends those 5 cents that now it receives from the relayer, sends them to attestation, tells the user to talk to the validators. The user goes to the validators, gets back the signatures and the SMSs, and again, funnels them through the meta transaction relayer because it needs to pay for gas because our user still doesn't have any funds at this point. And sweet, everything's done. And we have now this 2-layer mapping. Like before, we had the mapping directly from the phone number to an address, but now we have the mapping from the phone number to the smart contract wallet, and then from the smart contract wallet, we can follow the link to the signer. So when Valora is transferring funds, it's actually looking through this path to get to the address where the funds will end up in. Awesome, that's how we did it. And now let's look a bit about how this all is structured as an implementation. So Komenci, which means start in Esperanto, is the service that we build to help Valora start the user's journey and which orchestrates all of these smart contract to wallet operations that we talked about in the previous section. And it's not super complicated, to be honest, at the face of it. So we just have a user that has Valora installed on his phone, and Valora interacts with an API. That API is backed by a bunch of these relayers. Each relayer has an HSM, which is a hardware security module where it keeps its private key. This is just a security thing where the key is never outside of the hardware and signing always happening inside. So there's no way to kind of hack that relayer's key. The relayers interact with the chain, the protocol, they send those transactions, and they have the funds backed by this key to pay for everything that's happening. And we need a bunch of these relayers because, as we know, when interacting with the blockchain, all transactions that come from a single address need to have a sequential nonce. So you kind of have a limit on how much you can parallelize execution of a lot of transactions until you hit some weird behavior. So it's much better to have multiple relayers that are actually executing transactions on chain. And of course, the system has to be robust. So like if one relayer goes down, the system will still work correctly. But if we talk about this, like, okay, what if the API goes down? Well, of course, we actually have different clusters that have different relayers, APIs in different areas of the world. So we are robust to failure. Right now, we have 5 relayers running in Southeast Asia and 5 relayers running in Brazil. We chose these geolocations to be closer to our users in the initial launch, but we're gonna expand this set to cover more of the world. These are all backed by Kubernetes and are currently in Azure. We use that because it has a really good implementation of the HSMs, but we're planning on moving to AWS as well, so we can have relayers running on more platforms to be even more fault tolerant. Cool, but like this API could still be like used to just send a lot of SMSs or things like that, paid by us, even though it's not an incentive to actually collect any funds because you can't, but you can still abuse the system. Well, this is similar to any other solution as well. So we're using protection to things like CAPTCHAs when necessary, or device checks. These are just ways of ensuring that requests to our API are coming from actual Valora installations on actual devices instead of people trying to, leverage the API in unwanted ways. So yeah, like we were saying earlier, the relers actually have funds, and this is another way in which we're protecting ourselves is by not having the relers manage a lot of money at any one time. So if there's anything weird in the system that happens and it starts draining the funds on the relers by executing a lot of transactions, they will always have a very limited amount of money to drain. And we have another service which is outside of the internet. Essentially, it's not accessible to our users, which is actually managing these funds. Because, from a security perspective, if you look at the flow of information, you have the user that sends data to the API, and the API sends data to the relayer. So the relayer is one way or another exposed to user input. Even though we do a lot in the meantime to make sure that nothing bad can get to the relayer, there's still a path from the user to the relayer. But the fund manager that actually manages more money, there's no path from the user to that. So that's how we tackle the safety of the system. Cool. We went through Komenci as well, but now let's talk a bit about what we built and kind of what it means for these to be free. Because if we take a step back, we looked at the centralized service scenario and how that is structured. And then we talked about how Celo is different because we're decentralized, so we want to maintain those invariants. But what we kind of ended up with is a place in the middle. We have this service that essentially acts as a centralized service, but on the outside, it's interacting with the same decentralized protocol and the decentralized identity protocol that we built. And the invariants of that system stay the same. So any other participant in the network can interact with the same protocol under the same ways, and that keeps the decentralization. Even if for Valora, we chose to have this service, which is a bit more centralized in order to have this better user experience, because in the end, that's what we started from, right? We have to kind of find a balance between these. Not everything has to be totally centralized, totally decentralized. But at the same time, we are thinking about it. Like we built this as an initial proof of concept and solution for our problem, but we're looking at ways to actually expand the usage of this and potentially decentralize the transaction relayers and have anybody who's participating in the Celo network actually be able to run a relayer. But there has to be a marketplace for that. And also we're thinking about maybe the subsidy fund can be community run, but there are some incentives there that are harder to align, and we're still thinking about that. And we didn't want to solve too much up front. Basically, we wanted to improve the user experience but leave room to improve the solution in the future. Of course, we're also taking into account what's happening on Ethereum, like the gas station networks and any sender, which is a protocol that really inspired us a lot, and how to structure the meta transaction wallets. Yeah. And to kind of end, I wanted to give a bit of an overview of what's happened so far. We've been live with this service since the 20th of November. So it's 3 weeks now, I think, or something like that. So since version 1.5.5 in Valora. And since then, we've actually subsidized close to 3,000 attestations, executed about 8,000 meta transaction, and deployed 1,000 smart contract wallets to the network, which I think is super cool. And it all worked very nicely without any problems. And it means that we have around 1,000 users who onboarded using the new Feeless version. And yeah, they're running Valora now with their phone number attested. So that's pretty awesome. Cool. I'm gonna give it back to Julie so she can talk about the next Celo talk, which I actually super recommend because Kobe has been doing awesome things with Plumo and the whole crypto team.
Yeah. So Kobe, who is a crypto engineering lead, he's going to talk about Plumo, briefly go over recapping on what Plumo is, and then we're going to walk through the Plumo ceremony and how you can also participate in the Plumo ceremony. And I'll be doing the live demo with Kobe, so be sure to register and then check it out next week. And let's move on to the Q&A.
Awesome.
Cool. We have only one question. So can a bad actor, a validator, well, we wouldn't call it bad actor, equate that to validator. I mean, validator is validator. But can the bad actor flood the network with a request, attestations, and print money?
Let me see how to think about it. So I'm not sure exactly what you mean by printing money in this situation. Can you expand on that? Because he doesn't get anything from doing that. I mean, how does he get money? I mean, he could in the past, even without taking this into account, he could have like requested attestations, or maybe you mean what I talked about at the end, the fact that in order to actually interact with the API and request this free attestation to any phone number that you want, you'd need to pass some checks. So there is a cost associated with actually requesting a free attestation, which is the CAPTCHA and the fact that you are on a device that's validated. It's kind of the same thing that's stopping you from spamming Uber or whatever other application with the requests for SMSs, kind of.
Yeah, but validator themselves wouldn't be able to print money. I don't think printing money is not a.
So if a validator were to request SMSs on the system that he doesn't intend to deliver, he would receive the funds for that SMS, let's say, and he would not deliver the SMS. But there's like one other thing that actually is keeping them from doing that: the fact that there's no way to know what validator gets the request. So there's a randomness involved there when selecting the three validators. So he would basically need to request a lot of validators for everybody, and yeah, he just doesn't have any way to do that in a way that's spammy to the network, because it needs to go through phones, and yeah, the cost of that is way too big for him to for those 5 cents that he gets per validation that actually lands on him. So okay, we have a follow-up. Since are transfer to 3 validators every time an attestation is requested. That's true. Yeah, but you have to understand that during each time there are about 100 validators in rotation. So when you do one request, it picks 3 random validators from that set. So 100 requests actually gets you 5 cents theoretically, because that's the chance of you being picked for those 100 requests, if that makes sense. And Mircha is saying, could an existing Valora user vouch for their friend by acting as a relayer? Oh, so you mean essentially if you could forward a meta transaction to one of your friends and have him execute it for you, in a kind of acting as a relayer, or is that what you mean by vouch? Yeah, I mean, it's possible by the system. We don't have anything implemented in order to do that, but yeah, that could be a way. We in the past we were actually doing something similar, something not similar, but before we had this system, we had invite codes. So when you invited somebody, you actually bundled 15 cents with your invite in order for the user to be able to onboard. Well, not 15 cents, a bit more than that, in order for the user to be able to onboard when they redeemed your invitation. So this was kind of like an interim solution, but it's still weird to have a cost associated with inviting somebody. But yeah, this is sort of related to what you mean, but not exactly. But yeah, that's an interesting thought, like having your friends kind of act as relayers for you and pay for your transactions when you're onboarding. We haven't considered that, but it's an interesting thought.
Any other questions, folks? We have one more question.
How are the user proxy smart contracts deployed? Yeah, that's also handled. I glossed over that aspect, but that's also handled by Komenci, and actually the relayers execute that transaction. We have a factory contract that deploys the proxy, setting the right implementation, and sets the user as the signer for that implementation. And we have upgradability in mind, and very different, like each version of Valora is tied one-to-one with the implementation of the smart contract wallet, and it requests a deployment of a version that it knows about, and our service takes care of validating that that's an actual implementation and deploys that to the chain. We also verify throughout the process, both in Valora and in the backend, that the contracts that we're interacting with have the right implementation, that we accept, like all the proxies are the right implementation. Oh yeah, and there's one more thing that I forgot to add to the slides, and it's related to this, the fact that we're actually going to get deeper into the use of these smart contract wallets, which will power recoverability for our users, which is like an interesting thing that's coming next. Which means that if you lose your phone completely and don't have a backup of your private key, you can have this smart contract wallet be approved to move all your funds, for example, and have a mechanism of becoming the new signer of a smart contract wallet that you owned previously by registering people who can vouch for you in a like distributed key sharing sort of scenario. And that's like another interesting use that we're planning to put in for these contracts.
All right. Any other questions, folks? You made it so super clear, Bogdan. No questions.
I know, right?
Thank you, Alex and Misha, for asking questions, and thank you, Bogdan, for coming to Celo Tech Talks and giving good overview of a Feeless Onboarding.
Thank you,
Right.
Julie. It's
Thank
been an
you.
honor.
Yeah. Thank you, everyone. Have a good weekend. Bye.
Bye.